All right. Well, we're waiting for a few more people to join. And this morning we're going to start, well, today we're going to go through a lot of the programs. Let me just say that it helps enormously if you read the manual, and you'll see some things in the manual that will explain a lot. Today we're going to go through most of the programs, not all of them, most of them, so you can see roughly how to use the GUI. All right, well, we're going to start with rel test. There we go. Everybody can hear me now. We have quite a few people. I think we'll start. So let me see. We're going to start with the data quality relationship testing using the program rel test. Okay. And the whole point is that the relationships that are recorded may be wrong. Many SIB pair sets inadvertently contain relative pairs that are not full SIBs. Furthermore, if you don't exclude the non-SIB pairs, you'll lead to incorrect conclusions about linkage. So we need some methods to accurately determine true genetic relationships, and that's what rel test does. You can use the marker data to check relationships, and rel test uses IBD information but does not require input from GenIBD, I mean. So now let's look at these statistics. The statistic YJ for distinguishing relationships. Statistic YJ is the average number of alleles shared identical by descent -1 divided by the standard deviation of this in your sample. So if you think about this, this will be very small for unrelated people, or it'd be 0 for full SIBs and parent offspring. It'll be smaller for half SIBs, smaller for cousins, and as I say, very small for unrelated people. And sorry, it'll be bigger than those. It's bigger than the unrelated will be very small, cousins not quite so small, half SIBs not quite so small, but the full SIBs and parent offspring will have expected value 0 and will be smaller than for monozygotic twins. So this statistic YJ can separate out everything, except it cannot separate full SIBs from parent offspring relationships. So we have another statistic, YJ star, and that is the average of sharing of 2 alleles plus sharing of 0 alleles minus sharing of 1 allele. Also, this divided by the standard deviation in your sample. And in this, for this statistic, the parent offspring, the parent offspring value of this statistic will be smaller than that for full SIBs. Okay. So is this where you take over, Yanju?
Yes.
Okay.
Yeah, now we'll go over, just like before the previous programs, that what we need to run the rel test program, which now previously we didn't need it any of like a genome map file, but we covered how to actually construct, make like S.A.G.E formatted genome map file. And also another file that we talked about previously is the marker locus description file, which has the allele frequencies and the phenotype and genotype relationship between markers and phenotype. Okay, so you need the pedigree file, pedigree data file, parameter file, genome map file, and the marker locus description file to run rel test. And then it will give you the error file, .inf file, and all the analysis result file. And one more file that is generated is the genome.inf file, which is another information file that is generated whenever you use whenever the info file includes the genome map file or the marker locus description file. It is automatically generated. It is called the genome.inf regardless of the program that you are running, and it contains the alleles and genotype frequencies. Okay. So we'll go to the demo. So rel test can use a single or multiple data files in terms of like a pedigree file. Okay, because sometimes we do have like a separate pedigree file for each chromosome. So what the rel test does is you can actually give the multiple pedigree file, let's say like per chromosome, then it will automatically combines all the data from the different chromosome into one, because what we need is a genomic information to actually compute that YJ and YJ star statistics. So it can have like a multiple data file, and then only considers relative pairwise, and it requires genome-wide data, which I just talked about it. And so that's why it requires genome file, which is the genome map file. We look at this one, just like we said before, you can actually start the rel test in this way. From the analysis, click the analysis, and then bring out the data quality, and then go to the relationship testing to go to rel test. Then it brings to the familiar, the interface now it should be, and then we do drag and drop the marker locus description file from the internal file that we imported when we were creating the project. Okay, then this is the analysis definition.
Yinju, are you advancing your slides?
Yes.
Okay, because I just see the same slide. I've seen 3.6 up for some time.
I see. Maybe it's going a little slow on your side.
Maybe. Okay.
Yeah. I'm at right now I'm doing the slide 8.
Okay, well, maybe I've got the wrong one up, but that's okay. Just continue. Sorry.
So in this analysis definition panel, you see you can actually select the pair type to analyze sibling or half sibling, a pair of sibling, or the medical. Also, from your genome map file, it will automatically pop up all the regions that are specified in the genome map file, and also you can, it automatically computes the cut points, but you can actually give your own cut point as well. Okay, if we blow up start, you can see little bigger ones. Okay, that's the analysis definition options that rel test has. So once you run it, then this is the summary file that you get, which Dr. Elston will explain.
Okay, I see it now. For some reason, I was seeing the wrong slides. Okay, so this is just a summary file. It says default analysis, and you can see it talks about the average marker information content that was as defined in a paper by Lander and Krugliak, or Krugliak and Lander, I can't remember. And then if you look at the cut points, you see that you have the original and the adjusted. And the whole point is that rather cleverly, the program can tell that you've got a little shift here. And so it will give you these classification statistics. And if you look at the bottom, you'll see there's a warning. And it says the mean of the SIB pair distribution differs significantly from 0. You may have substantial data error or misspecification of parameters such as allele frequencies. Well, it so happens that difference between the original and cut point, adjusted may be significant, but it's really quite trivially small, as you can see. So let's go on to the next slide. This slide shows you how the pairs are reclassified. And you can see that, first of all, the putative SIB pairs to be reclassified. And here they are. You can see that there's a half, one SIB pair is reclassified as a half SIB, and then 3 of them are reclassified as MZ twins. And then down the bottom, you can see putative mother-father pairs to be reclassified. And it suggests that they are all half SIBs. So let us go on. And what this program does, it draws this little histogram. And you can see in this histogram that there's 1 point, well, you can see the full SIBs, that's the major distribution. And rather cleverly, we'll talk about tomorrow, you can see one outlier way at the top, and that is a, let me see, that is unrelated or half SIBs. Those are half SIBs. And if you look down the bottom, you'll see one way down there, and they monozygotic twins. Okay, so if you look at the parent offspring histogram, the YJ star, the full SIBs reclassified as parent offspring pairs, if present, would have a large negative statistic. There aren't any here, but if you look, you see all the full SIBs, and you see one way down the bottom, and those are MZ twins. Okay, is there some more output? Yeah, so you see which ones have to be reclassified, and it tells you everything. Okay, let's go on. And then for the parent offspring pairs, you see similarly, you see which ones, you see the maximum, minimum, and the bin size is set at 0.25. I think you can change it, but I would never change it. And it tells you the maximum value and the minimum value of YJ stars and the bin size you're using, 0.25. Okay, the detailed file gives you the putative SIB pairs to be reclassified, and also the putative half SIB pairs to be reclassified, and it's all there, and it gives you all this information. And if you look at this, oh, it's gone. There was the particular, it's telling you that this pedigree ID with this, that's the pedigree ID, and this individual in it, which you said were full SIBs, but it's telling you no, they're half SIBs, and it gives you the 2 statistics as well. Okay, and we have the putative parent offspring pairs to be reclassified, and it tells you those. It tells you those. It gives you the pedigree ID and the pair number and so on, and you get all this information down the bottom. Right. So now you can get the information per family. That means nuclear family here. And I don't know if there's anything particular to look at particularly here. It just tells you what the YJ was, what is after reclassification, and the YJ star. Okay. Now we're going to talk about allele sharing estimation. This is the GenIBD program. So what this program does, it generates identity by descent sharing distributions from family data and genetic marker loci by an exact IBD analysis using single or multi markers. It does it empirically via Monte Carlo sampling, and it can also, it provides sharing distributions for the following pairs, and these are siblings, half siblings, avuncular, grandparental, first cousin. And what it does, it lists the probability of each pair sharing 0 or 2 alleles identical by descent at each locus, conditional on the marker data available, as well as a parent of origin sharing probabilities. That is to say, the probability of sharing one maternal minus the probability of sharing one paternal. The output files to be used that you get here, you use them as input into other S.A.G.E programs. So this GenIBD is purely to be used for other programs such as linkage and relative testing. So this is where you take over, I believe, Yunju.
Yes.
Okay.
Yeah, just like the REL test we just talked about, GenIBD is another program that you need like a full set of the S.A.G.E, the input files, which means the data file, parameter file, and the locus description file, and the genomic map file. So using those, GenIBD creates do the IBD analysis and then gives you the INF file again, and something that is called .IBD file. So this is the file that has the IBD statistics, IBD values from the pairs, those 5 different pair types that we just talked about. And then since we use the genome map file and the locus description file, it will automatically generate the genome.inf file as well. GenIBD program, we are going to actually use there are like a single point and multi-point, and then it can simulate when it is greater than 22 bits, but it's depending on the system you can use. I actually was be able to run up to the 28 point without actually cutting while doing simulations. So, but when it is generally greater than 22 bits, it goes to the simulation, but you can actually put those numbers, and then it outputs all relative pair types, and then estimates IBD sharing at markers, and if in case it is the multi-point, in every 2 centimograms in between markers. So once we start the project, we can actually start a GenIBD job, and then you can actually see the genome map file is not there, right? Because internally, when we, like, let's say we created a project, but we didn't import any map file there. So then you see it will error out like this. Right in here, you can actually, another way, since we didn't import the genome map file, what you do is in here, you can actually go to the location by clicking the 3 dots there and go to the location and then specify the genome map file. You can populate your map file right there. Okay, then it will go to the analysis definition panel. In here, you see the title. You can name anything. You can type in any title. By default, it will automatically put the analysis 1 as a title, but you can name it. Okay, and just like before in well-test, from the genome map file, it automatically pops up all the region that is specified in genome map file in this region. Okay, and then if you want to, let's say, change your IBD analysis to just to do the certain chromosomes only, you can do that by just clicking it out and then just select the one that you would like to run your GenIBD analysis. Okay, then in here, next, after you specify the region, or you can just leave it select everything. And then in IBD mode, you can select either multi-point or single point. And then scan type is the one that you specify whether you want to do the markers only or the include intervals as well when it is the multi-point. With the SNP data, it doesn't change much because SNPs are usually with the SNP chip, they are really close. But with the let's say like a microsatellites, by doing the intervals, you actually get more information out of it. Okay, then you can specify output pair type by default to all relatives, meaning covering all those 5 different pair types. Or you can just select if you want to do the SIP pairs only, you can select it too. And whether you want to use simulation or not when it is bigger than the like a 22, let's say. Okay, if you choose to do the simulation, what you do is actually you can right here maximum bit is by default is 22, but you can change whether you want to split the pedigree or you want to just run it as it is, or you want to allow the loop or not. Those options you can specify right there. Okay, then you click run, then this is the output that we get. Okay,
so you can see the top, it tells you what you've done. Hold on, let's get this straight. You can see the default is to use sampling if the family has more than 18 inheritance vector bits. We'll talk much more about that, what those inheritance vector bits are on the next day. It says use simulation no here, but typically when that's typically you'd want to not say no there, and then you get this output here underneath. Whoops. And you can see all the markers one at a time, the pedigree ID, the individuals, and the markers. Okay, so it tells you, you can see, go back one, please. You can see on the bottom half, it gives you F0, the probability of sharing 0, the difference between the mother and father, parent of offspring, and then the F2. It gives you all those bits of information. Okay, now we'll go to the next one, and it tells you, first of all, what you're analyzing. And as I said, if the pedigrees are large, using simulation will significantly actually reduce the computing time. It wasn't done here, but typically you would do it. And then you've got, you'll notice the location starts at 0 always. And then from then on, you've got the distance between the intervals between successive markers. And in this case, yeah, successive markers. You can also do it intervals as well. And you can see markers. Okay, so now let us talk about model-free linkage analysis using sibling pairs. Let's consider an example. And this is going to be an affected SIB pair example. Now, affected SIB pairs are expected to share more animals identical by descent than by chance if you have, at a particular linked locus. So the null hypothesis you test is the mean sharing 1/2 versus is it greater than 1/2? And that mean sharing probability of mean sharing alleles identical by descent is the probability they share 2 alleles identical by descent plus half the probability they share 1 allele identical by descent. So we can also test, we can say, well, do the probability they share, the estimated probability they share 0 and the estimated probability they share 2, is that equal to 1/4? Because if there's linkage, you will see that these change. In particular, for affected pairs, the sharing of 0 is going to be less than 1/4, and the sharing of 2 is going to be greater than 1/4. For discordant pairs, it's going to be the other way around, and for unaffected pairs, the same as for affected pairs. And we always use one-sided tests. For affected pairs, testing this F2 is sometimes called the proportion test. There's a whole literature on it. We do it here just doing one-sided tests, and if the full SIB-ship is size greater than 2, this is the interesting part. So in samples with large numbers of SIB-ships, now we're just talking about SIB-ships, we can analyze the data as though all pairs of SIBs are independent. In other words, if we have 3 SIBs, there are 3 SIB pairs. If there are 3 times 2 over 2, if there are 4 SIBs, it's going to be 4 times 3 over 2. There are 6 SIB pairs. If there are 10 SIBs, there are 45 SIB pairs, 10 times 9 over 2. So now if you consider 3 SIBs, these are SIBs, let's call them A, B, and C. And supposing at some particular locus, the proportion of alleles shared identical by descent between A, B, BC, and AC, well, they're not independent, because clearly if A is identical to B and B is identical to C, then this implies that A is identical to C. So they're certainly not independent. But the most interesting thing about this is that they are pairwise independent. And therefore the variances and proportions of mean allele sharing are consistently estimated. Okay. So consider what's called the mean test, or with lots of different mean tests. But the usual one is we test that the estimated proportion of genes identical by descent is 1/2. If there's linkage, then for affected pairs, this is greater than 1/2. For discordant pairs, in other words, it's just 1 affected in the pair, it's less than 1/2. For unaffected pairs, it's greater than 1/2. So we can now use we're going to use one-sided tests. And the mean test for a quantitative trait, and in a sense, you can consider 0 and 1 as quantitative. We use the Haseman-Elston regression approach, but I'm not thinking particularly now of just 0-1 traits, but in general, quantitative traits like lipid levels, what have you. Okay, let's suppose the SIBs have trait values x1 and x2. All right. Now let us define this y sub d as -1/2 times the mean corrected x1 minus the mean corrected x2 squared. Now you see those means cancel out, and you have the usual Haseman-Elston statistic. It's the difference between the SIB pairs squared. And if you put -1/2 there, then the slope is equal to the genetic variance at the trait locus. Of course, you are assuming a model here, but we'll deal more with that later. Now, let us also define, so YD is the Y for the difference. Now let's do YS, Y for the sum. This is exactly the same, but instead of a minus in the middle of the square term, you have a plus. This has exactly the same slope at the trait locus. But notice now the means, the mu's don't cancel out. So you have to know in some sense or do something about the mean for the X1 and the mean for the X2. In the original Hazeman and Elston, which was the YD, you didn't have to because it canceled out. But now if you're going to look at this statistic, you have to worry about it. So if you take half of YD plus half of YS, the slope is again sigma squared G at the trait locus. And this is the SIB pair covariance. So it doesn't matter which one you plot. If you have the right values, you'll get the same slope. So you can see that in this graph, the slope is always sigma squared G. And you can see where along the x-axis you have the estimated mean proportion of marker alleles identical by descent. What you need to really appreciate though is the YD doesn't depend on the mean, whereas the other two do depend on the means for the traits X1 and X2. Okay. So let's consider model-free linkage analysis using sibling pairs, and we shall talk about the program SIBPAL. Before we go any further, though, you should look at the manual, and you'll have to understand that originally in SIBPAL, we not only allowed for full sibling pairs, we also allowed for half sibling pairs. However, the way we allowed for half sibling pairs was not ideal, and nowadays you should never use SIBPAL for half sibling pairs. You should use RELPAL, which we'll talk about later. So nowadays we're only using full SIB pairs for SIBPAL. Okay, is this where you continue? I think it is.
Yes.
Yunju.
Yes. Yeah, to run SIBPAL, now we need another kind of input file, which is the IBD file. We just talked about it in GenIBD. So the GenIBD file from the IBD file from GenIBD is the input file, input file for the SIBPAL, and another program that we'll talk about later, the LATPAL, so which is the model-free the linkage programs. Then it gives you the INF file again, and the analysis result file, which is either .mean file or .track file. The extensions are like that. If it's the mean test you are doing, then it'll give you the .mean. And if it's the trait regression, then it will be the .track file. On top of that, actually, it in GUI only, not on the command line, it actually gives you another output file, which is just the familiar R script file with a .r. That can be used to actually plot the result from the mean test or the trait regression test. The first example that we will consider in this SIBPAL the program is that this is the mean test option. The affection status, which is the binary trait, will be our main trait of interest, and all other options will be left at default. And then depending on whether you did a single point IBD analysis or the multi-point analysis, you can use either one. In this example, we will use the multi-point IBD analysis for like a chromosome 9, let's say. So in here, So we'll go this route to actually how to bring the a SIPL job, go to the analysis, and then choose the linkage analysis. We'll go to the model free and SIPL to bring our SIPL analysis. Then now we popped up a SIPL job, right? And here you can see, since we wanted to do the mean test, I click the mean test option in here. Okay, in the analysis definition, you can either click the mean test or the trait regression test. Once you click mean test, it will bring to this mean test analysis, the panel. Okay, in here, what you want to do is actually we want to first designate our trait of interest, which is the affection status. Okay, click that. And then next is the marker. In this marker, by default, every marker that is analyzed that exists in your IBD file will be automatically popped up right here. So you can just do every like a marker location there, or just click any location, any marker location that you would like to analyze to the mean test. Okay, now we do have all those. Give us a little bit of a bigger view. In here, this is the location of IBD estimation, which I just talked about it. And in here, output option, there are a couple of different output options, but one of them that I wanted to, even though we said we leave like everything as a default, one thing that I would actually do is actually give us like a more detailed output, and the tab delimited options. That's the one that actually gives you the output format as a just the regular, like a Excel, or just a tab delimited one line for each location. So that's the file that is actually used in the R-script file it is generating. Okay, now we will see the live demo later, but for now, let's see the output file from the mean test.
Okay, so it tells you at the top you have the mean allele sharing IVD for full SIBs. Full SIB pairs conditional on a binary trait affected, and you see it at then all the what the various things are. Pi is the mean proportion of alleles shared identical by descent. F sub I is the proportion of SIB pairs sharing I alleles identical by descent. And then you can have concordantly unaffected, discordant, or concordantly affected. And you have the trait affection W1. This is the let me just say, this is the least powerful but the safest option to use. We'll talk a bit more about W1, W2, and W3 and W4 later. So this, in a way, is the least powerful but the safest. Okay, and you can see at the bottom for each marker you have what your pi is according to the proportion identical, mean proportion of alleles shared identical by descent, according to whether the pairs are concordant, 0 affected, they're concordantly unaffected, 1 affected, discordant, and 2 affected, in other words, concordantly affected. And in each case, you get a t value and a p value. And is this the one? I can't remember where we have, yeah. Please notice what you're supposed to be doing is comparing the estimate with what it is under the alternative hypothesis. So the estimate is always, in this test, is always expected to be half. But you can see for the first marker, or for when you're doing the mean proportion pi, then it's supposed to be greater than a half. You would expect there's linkage, it would be greater than a half for the if there's no affected, less than half if there's 1, and greater than a half if they're both affected. And then for F0, you will see there's similar what happens to this is like the proportion test. What you expect is less than or greater than or smaller than 0.25, depending on whether there are 0, 1, or 2 affected in the pair. So this is just a tab delimited output. This is just the script output that Yunju was talking about. This is the kind of output you can use in other programs to draw pretty pictures. Okay, the SIGPAL program, let's see. Do I continue here? Yeah, you have various options. You can do multi-point or single marker. You can do this. One option is multi-point and single marker regression. Now, you got to be very careful here. You can do, before we go on to I stop Yunju for a minute. When it's multi-point versus single point, that means you're using either one marker or you're using multiple markers to estimate proportion at any particular point. Now, there's a difference between single marker regression and multiple marker regression. Multiple marker regression it refers to the type of regression, not whether you're using single or multi-point IBD values. So this means, for example, multiple regression here would mean that you are regressing on not just one marker, but on 2 markers. And we'll see what difference this makes later on. Here we're going to look at the single marker. Trait is affection. The regression method we're using is W4. That's the most powerful method asymptotically. Unfortunately, it's also the least stable one. And we'll talk about, it's very important to realize that when you start using using W4, you're making lots of assumptions. I mean, you're estimating lots of things, as we'll see in the theory. And so when you try and estimate too many things by regression analysis, you will get instability of the estimates. In this particular case, we're going to look at IBD sharing for chromosome 9. Okay. So we're going to use here W4, the squared difference and mean correlated trait weighted, the sum with difference and sum weighted by the inverse of the residual variance and adjusted for non-independence of SIB pairs and non-independence of sums and differences. We are putting in all these correlations, and so that's why you may get instability, and we'll see that later on. This is where you take over, Yunju.
Yeah. Okay, this is the second example, which we now do the trait regression with the options. We just talked about it. So we, in the analysis definition panel, we choose the trait regression, then go to the analysis, the definition, the panel for the trait regression we are going to do. So the first we wanna make sure that we specify our trait of a main trait of interest by clicking the define there, and then by clicking the drop down arrow we choose the trait. Then also there as you can see that the blob mean is by default, that is the default, but you can choose others there as well. Then
let me interject, if I may.
Yes.
BUP means the best linear unbiased predictor, and that is probably the best thing to use always. That's why it's the default. Okay, thank you, Yunju.
Mm-hmm. And then now, just like we did at the mean test, we bring in the marker, which was read in from the IBD file that was given. Okay. And then in here, if you see the dependent variable option right here, by clicking this down arrow, we want to go to the W4 option. That's where you decide where you want to do the difference of like a trade or sum or products or W2, 3, 4. So we wanted to do the W4 in this example. So you will choose the W4 from the drop down menu there. Okay, then now the bottom there, we have like a different output options, so we can specify. We want to make sure that we get the like a tap delimited output as well, and then probably more detailed output as well as in some cases p-value, if it's like too small, it will just to give you the 0.0000. So maybe we want to put like a p-value in the scientific notation. That's what we choose to do. And then we get this, the trait regression output from the multi-point IBD file, but still doing the single marker regression.
All right, so let's look at this output. It's going to be single marker regression. We're just going to put in one marker. It's a binary trait, affection stated, affected is A, unaffected U. Now look at this weighting option, W4. Notice it is a capital W. The weighting options are W1, 2, 3, and 4. They are capital W's. Now look underneath it, it says W1 is 0.5. That's a different W. It's a lowercase w. You can read all about it. Don't ever, unless you have very, very, very good reason, don't ever change it. But you can. It's an option you have, but I would strongly suggest you never change it. So other options used, it's identity weights, no. Robust variance, no. Use the SIB-SHIP mean, no. Use the BLUP mean, yes. Best linear unbiased predictor. And you're not using a robust matrix of a robust variance, so anything might happen. The trouble is, if you do use the robust variance, then you will find even then nasty things can happen. We're using this example to see how nasty it can get. Notice now that it says negative intercept set to 0. Well, the point is you can't have less than 0 alleles identical by descent. Okay, you just can't have it. So what the program does is it says, okay, we'll set that at 0, we'll fix it at 0, and then find out what the slope is. It's a warning, but you know, typically it doesn't matter too much. All sorts of minor things can call that negative intercept to be less than 0, which is impossible. So we just set it at 0, and then you get the answers underneath. So in the detailed output, it tells us the model is you have affection of the intercept plus, and you'll notice now the first of all, in the top line, you'll notice that it says A plus D. This is assuming the genetic variance is additive and dominance. You can have additive alone, you can have additive and dominance. And now in the next bit, we see that the sample, we see that we have 502 SIBs. The number of SIBs used is 500, but the number of full SIB pairs is 675. Well, how can that be? Well, that's because you've got some SIB-SHIPs of size greater than 2. Remember, if you have 3 SIBs, you have 3 SIB pairs. If you have 4 SIBs, you have 4 times 3 over 2, 6 SIB pairs, and so on. So you've got some larger SIB-SHIPs here. Then you've got some information about the trait underneath it, and it tells you what the dependent variant, it just tells you a little bit more. That's general information for the trait. that you're looking at. Okay, now the next output, it gives you these every marker, and you can see you've got the number of pairs at that marker. You're going to look at the total additive and dominance variance. You got the estimate, the standard error, the p-value, and the nominal p-value. And you can see on the right hand side, they put 1 asterisk for 0.05, 2 asterisks for 0.01, and so on. You sort of looks like a little histogram. Let's continue. So you get the estimates at SNPs, and this is an example, you get it every 2 centimorgan intervals as well. So that's a nice feature. It's going to, if you like, extrapolate, well, not exactly extrapolate, really interpolate, that's a better word here, interpolate at 2 centimorgan intervals if you ask it to. Okay. And here is the tab delimited output. This is the one that draws pretty pictures. And it's got the, remember, it always starts at 0, then all the intervals, and you get the nominal p-values. And if you'd done simulation, you'd get those empirical p-values as well. Okay, so the options we're going to look at now are single point, single marker regression. The trait is going to be the square root of dBH. The mean we're going to leave at the Blunt mean. The regression method W4, remember that's the most powerful but also the most dangerous, and all other options left at default. Okay, take it away.
Okay, I was muted. We'll first see just a couple of slides, and then I will show you actually some live demo for this example. And in here, just like the same thing as before, this is the second trait regression example. This is the third example right here for the S.A.G.E program. So first, this is the case that we want to choose the quantitative trait, which is the square root over dBH. That's what we will choose. Okay. For the dependent variable, we will choose W4. Okay, then so when it's all ready, just to hit the run. Okay, then we get this outputs next. But do you want to see the output first and then go to the live? But I think we can. I can show you the live demo and then come back to the output slide.
Okay.
Yeah. Just wait a second. A little bit bigger. This is better. And here we wanna start a new project. Start a new project. We wanna designate the place where my new project goes. Right there. We'll call it live demo 3. And next, we are using the DBH data file. So we do have the file ready. So I will choose the third option. And then add. We have seen this before already, so it should be familiar for you now. So we want to find our parameter file, which is this case. Okay, and we want to add our data file. And then now in here, we can do add IBD file right there. But in this case, we don't have IBD file yet, right? So I actually want to show you the GenIBD, running the GenIBD first to actually be able to run the CPAP. I mean, I do have it, but probably it's better to see the GenIBD first. It's pretty quick. So let me stop right there and just import these two. But to run GenIBD, remember that we need the locus description file and the genome map file. So we will actually import the locus description file, which we generated yesterday from free program. Okay, and then also the genome map file that we had it. We did it in the demo, but also it's right here. Okay, and then next, now, so now we have this file all loaded in, and then GenIBD right there. Right here, let's see, it says that all these data files are missing. So what you want to do is just drag and drop to the place it should go. Right there. So now it is ready to run GenIBD from right here. So let's go to the next. And then in here, what you want to do is actually we are using the we will run the single point just to make it go really fast. Okay, and then we only want to do for now just for the one chromosome. So deselect everything, and I will go down and just select chromosome 9. Okay, and then since it is the single point, so select the single point, and it will be automatically do markers only. So even if you do say the intervals in here, it's irrelevant for the single point case. Okay, we're doing the all relatives, so we don't want to do any the simulation now to make it go really fast. So those are all irrelevant. Okay, then let me make it a little bigger so that you can see the pop-up window as well. Okay, let's hit the run right there. So making sure every options are correct. Okay. It's running. You see, it's running. And as you can see down there, see how quickly it's going. Done. So GenIBD file is ready for us to use. Now let's go here and then find our analysis, which is the linkage analysis. It's a model based and a model free, and we want to do the CPAP analysis, which brings to the CPAP. Now we have like a CPAP right there. We want to make sure that we pops up the category file, and now it says IBD file is missing. We have to find our IBD file from the output of GenIBD, which is this one. So we want to bring this one to there, right? So you can do that by drag and drop, or just specify from right here. Okay, let's go to the next. And then we want to do the trait regression right there. And then we want to define our trait of interest, which is the square root of DBH in this example. Add the trait, and then by default it is doing using the block mean. Okay, And then for the marker, we want to select everything in this chromosome 9. And then if you want to do some subsets of like individual, like sample-wise, you can specify right there using some indicator variable in your the data file, but we don't have that. And then we want to do the W4, so you want to change it, W4 right there. Okay, and then we are doing single marker of the regression, so we are going to leave it as a single marker as it is. We are doing marker by marker, that's what it means. Okay, and everything else, we want to make this to be come up. Okay. Okay, and then next, and you want to do the tree regression, making sure, right? And then making sure all the options that we have is correct. Okay, then it runs right there. So now it is running zipper. Okay, and then oh, see why it's going a little slow.
Well, it has to do a lot with W4.
Yeah, and also, I mean, you know, one thing that I kind of didn't mention is in your pedigree file, since we are getting our marker information as a form of IBD from the GenIBD IBD file, you actually don't need to have your original raw marker data in your pedigree file. Okay, so that the reason that it's taking a little longer is because I use the pedigree file that actually has the original raw marker data, which I didn't have to do it. You know what I mean? So that's why it's taking like a long time to actually reading in those marker data. I accidentally used the pedigree file. I should have used the one that without the SNP data in there. So that's why it's taking a little long. Oops. Okay.
Well,
but you know, I mean, we can start right there. It'll just run the everything, every marker location, and then we can go back to actually output file that, you know, it's going to generate. And then later on, I will show you what happened on this, like the output file right away when it's the next live demo time. Okay, let me go back to the slide.
Well, have you moved what you were showing me?
Now I went back to the slide share. From this, okay, we actually get the output files like this, which Dr. Preston will explain.
So this one is just one marker. It's got the model in it. It's got the number of SIB pairs, number of SIBs used, the number of full SIBs, and the just the traits of information about the trait. That's in this one. Now, if we this information is just the trait distribution, telling you a little bit about it. Okay. Now let's look at this one. This is not relevant for that one. Oh, okay, it's giving you lots of detailed information. Let's look at the bottom. You have the information about the dependent variable. And then you'll notice it says what's the correlation in SIB pairs with no SIBs in common and the correlation in SIB pairs with one SIB in common. Well, what we assume is that the correlation, if there's one SIB in common, has to be at least as large as that for no. And so that's why these two are the same here. It was 0 for one, and we, instead of being negative, we just make it positive. We just make them both 0. And then you've got this detailed information. I'm not going to go into the W, but it's estimating W here for you. And you get the correlation in squared sum, between squared difference and squared sum, the mean corrected, and you've got that. And you've got all this information coming out. Now, if you use that script file, you plot something like this. And is this where we go? Are we continuing, or is it the break time now? I've forgotten.
I think we can go to the
Or we
break.
go on to 57. Okay, yeah. SIG-PAL program deploy, you've got options,
One more.
single regression, multi-point, square root DBH regression with, I thought that's what we just did, right?
This
Chromosome.
this is our third example.
Yeah.
Then we actually do the permutation test so that
Yes. So notice we're going to do the empirical p-values, and that is it's going to use a Monte Carlo simulation, if you like. And then it says max reps set to 10,000 and everything else left to default. And let's see what happens. We say max replicates set to 10,000, but it may not need that many, as we shall see in a minute. Yep.
Yes. So just like we saw before, this is where you specify the options to compute the empirical p-values by the permutation test. So we want to click the define right here to compute the empirical p-values. Then we do get this specification, the window right there. That's where we want to specify our threshold p-value to actually do the permutation test. So when it is the smaller than p-value is 0.05, we actually want to do the compute the empirical p-value. If it is the bigger than this, it will just skip. Okay, then we want to put our maximum permutation number, and then width of like a p-value and the confidence intervals. Okay.
Could I say something to
Yeah.
here at that point, the width of the p-value? This is telling you, and you have to read it more carefully in the manual, but it's telling you want 95% probability that the width of a you have 95% confidence that your p-value is within 0.2 with the width of the confidence interval will be 0.2. It's a little bit complicated. You can change those things, but only if you understand what you're doing. This is pretty good, that this default. Okay. Yep. Thank you, Junju.
Yes. Then we do get this output, which Dr. Elston will keep going.
All right. Oh, yeah. So this one, you can see it's got empirical. Now, if you look, you'll see you've got all the markers, and you've got in the regions, then you've got the centimorgans, the number of pairs. We're looking at the additive plus dominance. We're getting an estimate of the slope. We're getting a standard error. We have a nominal p-value. And we're also getting empirical feedback. The top one is interesting. Empirical is just slightly larger than the nominal one. And it's telling you how many replicates you have to do. Now, if the nominal is not less than 0.05, it's not going to do it because you're not interested. Why bother? So you've got all those markers there with nothing there. And then you see it starts, you can see about the 10th row down, we have a nominal p-value of what, 0.008 something, but when it does the empirical, it gets to 0.0067, and it did all 10,000 replicates. Now later on, you see it doesn't use all 10,000 replicates, and it only needed that many to give you that confidence that we were talking about. So it's rather smart in that way. Okay. And then you can get these, this picture here, which has different covariates. This is an interesting picture. I'm not going to go into the detail, but this is the kind of thing you can plot and show for different options on chromosome 9. So now it is break time. I'm not sure. Break time was supposed to have been what, at 11:15? Is that right? Or 11?
Break start from 11 to 11:10, but
Okay.
since Just to finish it, so briefly, I will go to the live again and then show you how to actually use the R script that it was generated to get that plots right there. Okay, let me share back my screen. Now, as you can see that it finished it. So it took just to actually read in the data as I was explaining. And once it read in, it's a simple analysis just to did really quickly. Overall, it still took only 3 minutes to get it all. Okay, so now in here, if you go back here, GenIBD now had, the simple in output, you see this simple.r script generated. So if you double click that one, it'll ask you the path of your R program, where your R program is. So you just browse the places that you want, you have your program. So in my case, I have it right at the C, there, my R program right there. And then I'm just saying this is where my R program is installed in my computer. So that's what I am saying right there. Okay. Also, it should be the path. So. Okay, then now it shows the script, actually what's inside of that R file. Okay, so it's saying the R script file is in these places, and then it'll read. If you understand, it's just pretty quick. So what I want to do is actually just to copy this part and then bring in my R program right there, and then just paste it. See, I just copy paste it, and then this is the output that you get. Since the example was a multi-point that I used, this was the single point that you can actually see a little bit of difference, like a more jagged outputs right there. But at least we see that the signal that we saw from the output file that actually right up there.
And we can see in this, it's pretty, it's pretty wild. And that is the first suggestion that you have instability. And we'll talk more about that after the break. Okay? Okay.
Okay, now we are back to our...
Yeah.
So we can actually write on time for the hour break, because our breaks, first break is from 11 to 11:10.
Okay. I'll see you later.